president of the Robot Car Federation for many years, and he has been named research leader for the specially promoted research project on constructive developmental science from the Japan Society for the Promotion of Science, and since 2013 is a director of the Division of Cognitive Neuroscience Robotics, the Institute of Academic Initiatives at Osaka, and is also in the board of directors of the Japanese Society for Baby Science. So his background and his research activity spans from humans to robots, and today's presentation is going to be how to develop artificial empathy, an effective and cognitive developmental robotics approach. Minoru?
Yeah, thank you, Julio. First of all, I'd like to appreciate all of you here because the final talk, the final debate, usually is many people leaving. Okay, anyhow, so as Julio introduced myself, the title is like this one, and actually this video I took the day before yesterday. So I arrived here the day before yesterday, and I walk around the downtown, and it's a very famous square, and the statue is a symbol of this conference. Okay, anyhow, so already Julio introduced myself, so I skipped this one. So first of all, I'd like to two prologues. First one is Leonardo da Vinci Android Initiative. So this is not the research itself, but the concept is Leonardo is a pioneer of interdisciplinary research, science, technology, and art. So the key word is interdisciplinarity. So if he were alive here today, he must be the researcher. And also this activity, the movement is to offer the liberal arts for the children and the junior by utilizing the Leonardo Android. But actually, in my mind, so to share the Leonardo spirit, there is interdisciplinary approach among the researchers from the different disciplines. The first of all, I'd like to show how to make the Leonardo da Vinci Android initiative. Actually, we brought this Android in the Science Museum in Milan. So that's the first exhibition of this Android. And the day before yesterday, myself and Julio went to the Milan, the Science Museum, and we had some talk event. So this is some kind of kickoff the meeting, how to design the Da Vinci Android, because actually so far the Android all the time real person, so we can measure the 3D measurement and then design. But this time, so designer think about what is the image of the Leonardo da Vinci. So for the Japanese people, the Leonardo da Vinci is the image of the very, very old one, the self-portrait of the very old image. So therefore, this is the first trial, and then we designed the very old Leonardo da Vinci. And it's just a painting, and also hair punching, one piece by one piece, and then the face is controlled by the pneumatic actuators. So this is assembling the air valve to control the facial expressions for the neck movement and so on. So this is a very, very quick the video, and then assemble it, and then testing. Okay. So you can control the Da Vinci Android. So now you can control the movement, the head movement through the iPad. So and then open the eyes. Okay. So this is the Leonardo da Vinci Android, and the most advanced technology from Osaka, from Japan, to the children all over the world. Okay. This is September 3rd, we have the press conference in Milan.
Leonardo da Vinci, ospite d'eccezione del Museo della Scienza di Milano. Il genio italiano è stato ispirazione e modello per questo androide con le sue fattezze, che è stato progettato in Giappone da Minoru Asada, direttore del Dipartimento Robotica di Neuroscienze Cognitive dell'Università di Osaka, e realizzato da uno studio di Tokyo e Lab. Le espressioni del volto e i movimenti del collo.
So I don't understand any Italian, so I skip this part. And that's actually, so this is the remote control. So the operator speak something, and automatically the lip shape, lip movement automatically generated, and then make some sounds.
un grande piacere vedervi.
Yeah. So of course this is not the research itself, but actually there's some technology we can utilize this kind of the technology to study about the emotion, the facial expression, and so on. So another one more proof is that the RoboCup. I'm one of the founder of the RoboCup. So in RoboCup, we stated that the founded in the mid-90s has been the vehicle to promote the robotics and AI research by offering the publicly appealing but formidable challenge. The building a team of the robot in the environment with great uncertainty, such as rescue. We have the significant social and economic impact and reaching the specific circa 2050. So the final goal of the RoboCup is to build a team of the 11 humanoids that can get a win against the FIFA World Cup champion team. Very, very, very ambitious. Okay. That will certainly be considered a major achievement for the scientific field of the robotics and AI. But not simply the robotics and the AI, but more. I mean the cognitive science, neuroscience, psychology, and so on, to give such a real impact to the society. So this shows the number of teams in RoboCups. So it seems to be saturated, but actually, due to the limit of the time and the space, we limit the number of the teams participated. So therefore, but actually around the world, the number, participant number of the, they participate in regional events is increasing. One more thing I have to mention is that the half of the teams from junior from the elementary school to the high school students participate with us. So they have the dream to achieve the final goal. So actually 2 years ago, my own team got the Best Humanoid Award and, in the Adult Size League. And the Best Humanoid is supported by Ray Vitton, and it's the Baccarat crystal. And 1 year, that crystal was exhibited in the president room of our university. I'll show you some digest. So 2 years ago, we had the RoboCup in the Netherlands, the Eindhoven. So the queen visited us, and this is local team. So the people are so excited. Again, just everything is automatic. So if they manually control the human team versus the AI. So this is the middle-sized league, most exciting and the largest field. So not only the soccer, but also this is the RoboCup rescue. So in this case, the teleoperation. So but the sensory information only through the robots. So the team's competition is just to find the victim of the doll or to capture the situation, the situation of this one. Okay. Yeah, sometimes drone is used. And let's see, where is my, okay. So this is the RoboCup at work, so sponsored by the Fest. And some teams, competitions, carrying, found the industry parts, carrying them and assembling them something, okay. And this is a small size league. It's a very, very quickest movement. So the marker is just the TV camera from the ceiling and to detect the position and the kicking. So it's very, very quick. So therefore, it's very difficult to follow, to track the ball. This is a simulation league. And this is available now. And nowadays, this is a platform for the research in the human-robot interaction. So in this case, the 5 now is still unstable. Yeah. Okay. But the team tried to program the behavior to stabilize the movement. Or some teams designed by themselves. This is a team size. It's very unstable. And and kicking. So these are the soccer application, but also we had the RoboCup at home. So how our technology, developed in the soccer simulation, the soccer game, can be applied to some daily life application. The rescue is non-daily life, but the RoboCup at home is daily life application to identify the family member or to communicate with people, to assist some the physical task and so on. So the RoboCup at home is one of the aspects of the future image, future society. So by using these technologies, we may have some future symbolic society with robots. Okay, robot can with us, assist us every day, every time. But towards the future symbolic society, So the robot should assist our lives, of course. But in addition to the physical assistance, the mental assistance might be more important. So from simple special purpose machines, like a Roomba or the cleaning robot, to multiple purpose human-like existence, so like a partner or the family member. In Japan, we have the Doraemon or the Astro Boy as just the typical one, the partner of family members. In that case, to what extent should the robot understand our behaviors and the intentions? Or to what extent should the internal mechanisms of robots be close to us? But to begin with, do we have the same mechanisms as everyone or not? So that's the question. So the purpose of my talk today is that the grand challenge is to authentically design and build a human-like existence. But of course, authentic is another buzzword to loosely defined. But anyhow, so art for empathy is a symbolic goal involving the many essential issues such as mirror neural system, self-other cognitions, awareness, self-mind, and so on. So today's talk is not to show the success stories, but to show the limitation and gaps we are suffering from, and to share them in order to start more collaborative studies by a team of researchers from different disciplines. I suppose maybe the cognitive science is kind of such a role. The cognitive science should have such a role of to push the interdisciplinary approaches. So in my talk, what does robotics mean? The first one is the design theory. So we are taking the constructive approaches to the cognitive issues by utilizing the virtual and real robots. So the existing discipline try to explain the mechanism, or explain the phenomenon. But our side is to design, okay? So we have some weapon to design and to build up something. So that's a design theory. The second point is the developmental aspect. To not give them a priority, but obtaining through the learning and the development process as much as possible. Of course, it's very, very difficult sometimes, but just a challenge. And third one is robot as a tools. So yesterday we had the symposium, and also we are discussing about what is the cognitive robotics. And one of the role of the robots, cognitive robotics, is that robot as a tool, as a stimuli for studying the human's behavior and demands. Okay, so we are focusing on the development process. So, horizontal axis shows the temporal, the time one. The vertical axis means some complexity, intelligence, functions, and so on. So the ordinary people maybe go through some pathway, a little bit different, each individual difference may happen, but almost similar, the pathways. But sometimes, the patient, like ASD or some other different disorder, the different pathway, like this one. The robot may have a very simple straightforward functions. So that is straightforward, okay, existing robotics. But my desire is to design the robot that can almost follow the human development process. That's my idea. So the outcome is the sharing the goal. So outcome is very similar to each other. But sometimes the method or the approach or how to implement might be different. But sometimes some key process may share, the sharing process may happen. Therefore, I suppose maybe not only the goal sharing, but also having some intermediate process is important to design our robots. Okay, this is our talk, and also I have done already the prologue. And then from now on, I try to explain the cognitive robotics and some concept of the artificial empathy, and the two studies and summary on the future issues. Okay, so what is human development? So I was born 1953, and I went to the elementary school, junior high school, and high school. I entered the Osaka University, and I got a job in the Osaka University. I stayed 1 year in the University of Maryland, and this is the first RoboCup. And in 2009, I enjoyed the karaoke in Shanghai. So this is a typical human development. Okay, I'm just kidding. Okay, so what's going on in the womb? So this is the fetus. Nowadays, we can see what's going on in the womb. So the stereosonor image visualize the movement of the fetus. So the left side is 26 weeks after the conception. So you can see that fetus touch so often the face and so on. And 36 weeks, just 4 weeks before the birth, and then open the eye, open the mouth, and some coordinated movement of the hand to the mouth and so on. Okay, and after the birth, so the newborn baby obtained shows the different behaviors. For example, at the 5th month, the hand rigor doesn't look at the hand. Okay, from a viewpoint of the robotics. So in case of the hand rigor, it means that it's learning the forward inverse model of the hand. The forward model is just if you specify this angle, this angle, this angle, you can specify the final posture of this hand. This is the forward model. On the other hand, if you try to grasp this one, what kind of angle here and here and here, this is the inverse model. So at the 5th month of the newborn baby, they seem to learn the forward and the inverse model. Or the 6th month or 7th month, the different behavior or different. At the 10th month, the imitation is very, very important. And the final, just 1 year later, the 12 months, they have shown some pretended behavior. So from a viewpoint of the robotics, it's kind of a mental simulation or imagination. It's very, very high level functions. So we gave up to design such a robot just 1 year. Just the newborn baby obtained a different kind of behavior just 1 year. But the robotics researcher gave up to design such a baby robot because we do not know how the baby learned to this kind of behavior. That's a big, big mystery. Well, someone says that everything is nature, everything is gene. But the next question is how to code it into the gene. So this is a classical the paradigm, the nature versus nurture. So the Matt Ridley mentioned that nowadays you have already known the nature side and nurture side is closely related to each other in the different levels. So therefore, no longer it is nature versus nurture, but nature via nurture. For us, a balance between the nature side, the embedded already, and nurture side, expecting learning and development is one of the issues. From when we start, from fetus or from the kids, the newborn baby or something. So that's one of the issues. So we have, not my own self, but also myself and Julio and the other guys to publish the related books and the papers about the cognitive robotics. Okay, again, so the what's affective and the cognitive robotics, dependent robotics. So the aims at understanding the human affective and cognitive development process by synthetic or conceptual approaches. And the core ideas are the physical environment and the social interaction that enable the information structuring through the interaction with the environment, including other agent. The physical environment is not a new word, of course. Many, many years ago, the Roger Spelling, 1952, just 1 year of my birth year. So he mentioned that to understand the mind, begin with the patterns of the motor activities and derive the underlying mental structures from them. Okay, of course, he mentioned about the biological system, but we care about the artificial system. Also, the artificial system care about some physical environment. So existing robotic researchers that, of course, the robot exists, therefore a physical environment already, but actually not. So the robotics designer, researcher fixed the movement by the very, very rigid modeling something. Sometimes, some concept of the physical environment is lost. About the social interaction, I like to refer to this book, Out of Our Heads. So the Alban Noé is the young philosopher that the mind cannot be understood except in terms of the interaction of the whole organs with the external environment, especially the social environment. Of course, he has not mentioned anything about the design, but he is very, very good suggestion. Because everyone supports that everything inside the brain, but only single brain is very difficult to emerge such a mind. So therefore, the two robots or one robot and one human is a high possibility to think about some phenomena like a mind. So we have to design something mechanism to interact with other agent. That's the chance to emerge the mind-like phenomenon. Okay. So the approaches of the affective and the cognitive development robotics is just the two phases. One is that the construction of the computational model of the affective and the cognitive development. So the hypothesis and the verify and so on. This is a sort of the traditional approach one. The second point is also robot can contribute to as a stimuli, tools to study about the human, the science. For example, my former colleague, the Hiroshi Ishiguro, he is a guy of the Gemini, his own android. So he utilized his android of some psychological experiment because actually the experiment may be affected by the subject, but the android cannot be affected by the subject. Therefore, some systematic experiment can be possible. Therefore, the robot has some new tools. Of course, at the same time, we may have some another issue is that how robot can be the tools or something. Okay, so this shows my former project and starting the data simulations and numerical captures of the motor skill learning, the interaction, and so on. All the time I asked can robot physically grown up? Yeah, of course, with some way to type a robot researcher try to design, or some emerge some visions or ears and something, but it takes so long time, and we need more money and more people, so we gave up. Instead, we prepared several different kinds of the platforms depending on the age. And depending on the age, we focus on the research. For example, before the birth, just fetal simulation is sensory motor mapping in the womb, or 7 months, 8 months, the crawling, or the 11 months, the 1 year, the walking, or the more than or the 15 months, it's just some social interactions. So of course, still we do not have very consistent way to develop some cognitive functions or something. But still, we are just studying how the human behave or run something. These are the robotic platforms we have designed before. So the top left is just the thinking. It's a tabletop the humanoid and some social study, how the gaze affects some social communication and so on. Top right is some pneumatic actuators of the learning to crawl or something. And the bottom left is some motor skill, the walk learning by the human teachers. In this case, a sort of the co-development or co-learning between the robot and a trainer. And the bottom right is the imitation. Yesterday, Yuki Nagai mentioned this one. It's the beginning of the mirroring system or something. Okay, so our main topic is artificial empathy. Okay, so why I care that artificial empathy is it includes the self-other cognitions. About the self-other cognition, we just follow the NISA's definitions and just follow. We roughly 3 kind of stages. The first one is ecological self. So interaction with environment or synchronization with environment. So the baby finds its own body or some ownership of the movement and so on. And the second stage, caregiver enter in the situation. And in this case, at the beginning, the caregiver's body like as an infant body, so like me hypothesis, like this one. But gradually, the caregiver be independent, and then different from me hypothesis something. So in this stage, the mirroring system is an important infrastructure to develop the interpersonal self. And third one is a social self. So in this case, so the agent or can control synchronization or desynchronization freely. So these 3 kind of stages is just roughly we are imagining. So actually the day before it said Nicholas shows some kind of synchronization. This is 32. Yeah, much more. Okay, so it's kind of synchronization. Okay, it takes some time, so I try to. Okay. At the beginning, run down, and gradually, and finally, okay. This is the Nicholas shows, as shown already. Okay. So the same body structure is a sufficient condition for the agent to synchronize. In this case, 32 metronomes negotiated through the unstable plate. This unstable plate is very, very important. So entering into the attractor of the dynamic landscape of that situation. So in case of the living agent like us, unstable plate could be the sensor and the action modalities to mediate agents such as vision, gesture, and auditory speech. So not exactly the same body structure is needed. The belief that the opponent has the same body structure is needed to ensure the synchronization, even though it is actually not. So the interactive agent cannot verify this one. The typical example is the infant and the caregiver interactions. So this kind of synchronization, imagine as Okay, so we demand that, okay, that kind of synchronization, the mental synchronization is sort of the empathy. So I just borrowed some kind of the evolution of the empathy from the primate researcher, Debar. So he mentioned that the evolution of the empathy in parallel with the imitation. That's a very, very good news for us because the empathy is a mental situation or mental phenomenon. The imitation is the actual movement. But from the beginning, the emotional contagion, the motor mimicry, closely related to each other. Therefore, mental synchronization and physical body synchronization is very, very close from the beginning. And in addition to that, another one is also he pointed out that this axis so increase the self-other distinctions. So I upside down to the Russian model and then some physical embodiment and affective cognitive development and the social mind emerge. So along the the development process of the self, the ecological self, interpersonal self, and social self. So as a summary of the development or evolution of the empathy, I just show this image, the picture. At the beginning, okay, the internal state is just one agent inside one internal state. But due to the function or the mirror system, okay, probably I may have different how to say, not exactly one, not exactly two, but some, not major situations. In this case, the emotional contagion or motor mimicry may happen. Through the self-awareness, so its own agent, the internal state, and estimation of the other's internal state is separated. And the perspective taking, serial mind, mentalizing, the cognitive empathy happen. The so-called internal state of one agent and the estimation of the other's agent state is the same, okay, so far. So this is a definition of the empathy of my own. But emotional regulation, sympathy and compassion may happen. At the beginning, the same state, but shifted, a little bit different one. After that, two extensions. One is the in-group, out-group cognition, is that the self has some membership of self, and also as a membership, and between two groups, MB and Sharon may happen. Another one is that, okay, so the estimate of the internal state of the others, again, inside own. So this is a metacognition. So the passivity emotion, felt emotion happen. The typical example is sad music. We enjoy the sad music. Sad music perceived sad, but we enjoy the sad music itself. So that's a mixture of the passivity and the felt emotions. So we have done several studies along with this, the pathway. And yesterday the poster was there, and also yesterday symposium of the cognitive development and the architectures for the cognitive robotics. Yukinaga's and others talks related to this one. So again, this is the development of self and other cognitions, and this mapping of the development, the empathy. So today I focus on the two topics. One is some neural dynamics architecture, very, very fundamental, very, very primitive architecture of the neural dynamics. And the second one is just some social interaction. In this case, the motivation model based on the relatedness. The relatedness is also important to entrain, between the two agents. Okay, so the neural dynamics. We may start with some fetal brain development. I have shown the partially. So my former colleagues, Mori and Kuniyoshi in Tokyo, Yasuo Kuniyoshi was group leader of my own research project at the project. So, of course, make a baby is some classical way, it's very easy, but we cannot open the baby's brain. So they made the baby inside the computer. Okay, the very, very simple brain is the motor area and the somatosensory areas, and also the muscles. Each muscle has its own oscillators. So they build up some simple brain and the simple structure of the baby and in the womb. So the point is that, this is the neural system. It's a very simple brain. The neural system, the muscle skeleton system, and the environment interact together all the time as the same. And then this shows some kind of the graphics of the movement. Then you can see that some of the fetus movement inside the womb. And also the movement activity with M1 and S1. This shows the 200 the muscles inside the fetus, and also some tactile sensations. Lead means high pressure, so it means that self-touch so often in the womb. Okay. So by these simulations, they have shown some very interesting behavior or the body mapping too, and so on. So the question of this one is that, what kinds of network structure cause different behaviors? So actually, they have applied some kind of the chaotic element or the oscillations, and then everything together, the interactions. And they have shown some behaviors and mapping. But what kind of network structure happen and cause some different behavior? It's that question. So we try to analyze some network inside, okay? So the more conceptually, the chaotic itinerancy to understand the mechanism to emerge versatile behaviors from interaction between body, brain, and environment. The sequence of squash attractor in a high-dimensional state space of the neural activity. That's Ichiro Tsuda, my friend, and he is the famous guy of the count theory and something. So conceptually, some kind of the attractor, okay, and then stay one place and then another, the move around. So this is some kind of typical aspect of the dynamical systems, something. So we apply this concept to our interaction, body, brain, body, and environment. And as a result, we may have some kind of some result, outcome of the behavior. So in this case, a newborn baby or the fetus or some snake-like animals and so on. So the idea is that, okay, so the previous studies, that's with Kuniyoshi and Mori and so on, so they have shown some simulation with environment, you can see that, and sensors, actuators, and chaotic elements. So chaotic element directly connected actuators and so on. And they have shown some simulation like this one. But as you can see that, so we have the cortex, the more element. So therefore, we put more network, okay, which is not direct connection to the sensor and actuators. So diverse behaviors are spontaneously emerged by complex network connected to the muscle skeleton body according to the topology of the network. Okay, so the idea is that conductor simulation using the nonlinear theta network and the muscle skeleton body, that's some physical structure or some anatomical structure. So from the viewpoint of the brain science, that's a DTI image, so anatomical the connection, like this one. But through the interaction, we estimate an immersive network structure which behaves by causality between neurons. Just we say causality network, so analyze some transfer entropy or the causality analysis. So we have some information structure. Okay, so the left side is just anatomical, the physical structure. On the other hand, through the interaction, we may have some causality network that's quite different from the physical network. Okay. So the simulations, the fetus is so complicated. Therefore, we are using the very simple snake-like animals. So the number of link is 15, and the active neurons are 26, the hidden neuron 174, and topology of the wire network is a randomly distributed network, and simulation the 2002, and no learning mechanism yet. Okay. So we try to analyze the situation, the phenomenon. So as a result, we have, roughly speaking, two states. One is unstable, the stable states, just stay longer. On the other hand, second one is unstable one. Unstable means the duration is very short, so sometimes transient, immediately. And inside, we have some subnetwork structure in case of the stable one. So many subnetwork, and the coarse connection among them. On the other hand, in case of the unstable one, the whole network, just one network, together. Okay. So as a result, we got this one. So as a result, two types the phenomena, stable and unstable. And stable is a local connection, and the unstable case is the global connection. Okay, one more slide to show that. Okay, this one. The three major question is how are neurons interacted? In case of a stable motion, it's a local interaction. On the other hand, anti-stable motion is a very, very global interaction. What structural property of the causality network? So in case of the stable motion, less complex network. So network itself is a very simple one. On the other hand, unstable motion is a more complex network. How much the interaction is the local interaction, the stable motion is very, very weak interaction. On the other hand, unstable motion is a very strong, the connections. So roughly speaking, two states switch each other dynamically. In this case, we do not apply any learning algorithm. Just look at, observe the phenomenon. Okay. So the discussion in this case is a very simple environment and a simple structure. But if we have more complicated body structure, such as features and neuronate, including other sensory modalities such as vision and auditory, we may have more complicated network structure and more close to the environment. So one of the issues is the emergence of the switching module between the stable and unstable states. So in this case, we are arguing that what is the structure, what is the function? We may expect the subnetwork may correspond to some brain regions, but not the stable one, not the fixed one, dynamically changing. But roughly speaking, some kind of function may happen through this kind of things. Actually, the day before yesterday, there was a symposium of the neurobiology of the language, and many speakers agreed with that. So the classical viewpoint of the function of the brain region is one-to-one correspondence, but it's wrong. It's just average. Actually, time to time, so network structure changing. So actually, this guy, Louis Pessoa, he analyzed the kind of meta-analysis of the imaging studies, and he found that the classical viewpoint is the brain region, the function one-to-one correspondence, but actually not. So he has shown the diversity map of this one, how the brain region can be used in the different functions. The red means more functions. The red region is used more functions than the blue one. So this is a kind of support, okay, so dynamically changing situations. But my idea is that, roughly speaking, the stable and unstable situation happened. So my desire or speculation is that the consciousness comes from the unstable states, more interaction with the physical environment through the sensory motor systems and exploration and motivation. On the other hand, unconscious level is at a stable state, less interaction with the physical environment through the sensory motor systems. The chaotic and equivalency between both states with a huge diversity of the behavior is a phenomenon of the locked cell. That's my speculations. Okay, so this is a very, very fundamental, primitive the result. Okay, so I suppose that the next topic is some kind of sociality or social interaction. In case of the social interaction, we prepared, we suppose, we assumed many, many assumptions, but I try to figure out how the first study related to the second study. Okay, so this paper shows some social relationship and mortality risk, a meta-analysis, a meta-analytical review. Okay, so plus one. Okay, so there are many causes of going to die. The bottom is air pollution, or drug, or something, physical activity, and so on. But the top three is a social interaction. How the social interaction or social relationship is very, very important for our human society. So how the social interaction affects our life is a very important issue. So in the parent-child communications, emotions are evoked by the various types of intrinsic and extrinsic motivations. Those emotions encourage actions that promote more interaction. Therefore, the example is the infant, the caregiver interaction and the motivations triggers some new behavior, and new behavior triggers new interactions, and so on. So, okay, from now on, we first presented the emotional development model of infant caregiver interactions based on the intuitive parenting. Then, the motivation model in which relatedness, one of the most important basic psychological needs, is the variable that increases with the experience of the emotion sharing. And besides being the important factor of the pleasure, relatedness is a meta factor that affects other factors such as stress and emotional belonging. Okay, first is just emotional development. So another question I often got is that, can robot has a feeling or emotion? Often I was asked. My answer is, of course not, maybe. But my question, do you know how your feeling happened? No one can answer. So that's a big mystery. Okay. So in this study, we suppose that, okay, So maybe the infant or infant robot has a very, very fundamental emotional state, present and displeasant. Okay. So the point is how the agent, how the infant can differentiate the emotional, very, very fundamental emotional state to the normal one, such as laughing or the disgust or something. So we just borrowed some idea of the intuitive parenting. The parents often mimic and emphasize their facial expression of the certain emotional states, presumed from their children's facial expression. For example, okay, the baby just falling down, oh, crying, oh, yeah, baby, like this one. Okay, so the parents automatically reflect the infant's internal state and shows some facial expression. So we apply this idea to store, the facial expression. So infant gradually learn his or her own internal state, differentiate gradually through the interaction with the caregiver. Sometimes the big sound happen, oh, surprise. Okay, so the baby surprise and also the mother surprise. Okay, the baby supports that, okay, this face is a reflection of my internal state. And then gradually obtains, or differentiate the internal states. Okay, so the learning. Then after the learning, so we have some kind of the differentiate emotional state. So we're either laughing or something like this one. And after the learning, this guy just imitates the caregiver's emotional state. Because this guy, infant's guy, the virtual agent, has already learned to mapping of its own internal emotional state to the mother's. The mother's, my former students, shows an anger face, and then the robot tries to anger, right? So this kind of the empathy, some kind of synchronization happen. Okay, this is a very, very simple one. Very, very simple one. But I believe that such kind of interaction is very important for the infant to differentiate his or her own emotional state. This is very, very too simple, therefore no one believes that, but we need some kind of verification of some brain science or something. This is some kind of mapping or some kind of correspondence of the brain region, especially insular and anterocingulate cortex is very, very important role. Actually, I surveyed some empathy in the brain science, and many, many people, not so many, many studies just focus on the pain. And the pain matrix is very famous. But actually, of course, the pain is very important to survive. But for the human-robot interaction, we need more, some laughing, the surprise, or joy, or something. So to do more realistic interaction, we focus on the next one, is the relatedness. Okay, so motivation model of the interaction between the infant and the caregiver, which is relatedness. In fact, the relatedness, one of the most important basic psychological need is modeled as a variable that increases with emotional sharing experience. The emotional sharing is a key term. Okay, how much the caregiver and the infant is sharing their emotions. The proposed model is implemented in an artificial agent with a simple facial recognition that I have already explained. And the gesture recognition system. The baby-like agent successfully interacts with the actual human and shows a reaction like a still face paradigm. Maybe you know the still face paradigm. Okay, so caregiver and the baby interact each other. The first stage interaction, and baby, the caregiver, Jeffrey interact. And then suddenly, the caregiver shows a still face. And infants, at the beginning, try to interact, okay, yeah, or something. But there's no reaction from the caregiver. They gradually stress happen. Then after the reunion, okay, so the mother and the infant interact each other. So the relatedness is one of the issues of from the intrinsic motivation to the fundamental need or something, autonomy, the competence, the relatedness. And in this case, the dopamine has a big important role. So because the dopamine is famous for the prediction error of the reward in reinforcement learning, but in this case, it's related to the nervous signal, not related to the reward. So we set up the virtual agent and the humans, and we specify these kinds of the parameters. So okay, in this case, designer prepared this one. It's completely different from the first study, but anyhow. So the motivation model is referring to the existing studies. For example, the emotion sharing keeps the relatedness, or the novelty motivates arousal and attention, or arousal of the imitation goes up when the parent shows no response and so on. So we we try to make this statement to the computational model or something. So in case of the relatedness, so we have some kind of emotion sharing term like this one about the nobility of this one. So IT means some kind of mutual information to show the nobility. And the stimulus is also the other of the infant goes up when the parent shows no response. Therefore, the emotion sharing is minus the negative factor, or like this one, or the emotion mirror, or emotional expectancy, something. And then, finally, everything is formalized these equations. Oh, sorry. And then we started some learning process and interaction process. The same situation, and the infant already got some kind of emotional state of the calm, laugh, surprise, cry, and also the appealing behavior. This shows, some really learning results of the, so the infant ran the facial expression of the caregiver or experimenter, and also its own internal state, like this one, and the interaction with my former students. Okay. And then, some interaction, and then appealing. So the three-phase paradigm, so you can see that. So this is some estimations of the emotional state of the experimenter. And the right hand shows some relatedness of the virtual agent. You can see that before the three phase, so relatedness increasing. But after the three phase started, so relatedness is down and down and down. And the reunion and again. And also the virtual agent, the arousal and the pleasure is like this one. So increase in the relatedness invokes the pleasure emotion. In still phase space, the increase in arousal induces the increase of the action occurrence, the same as the 9 months infant response. Okay. So that we, of course, we tune some parameters, but anyhow, so some kind of reproduction of the still phase the phenomena like this one. So the 9-month-old infants are more sensitive to the still phase than 3-month-old infants. The 3-month-old infants show only negative response, but the 9-month-old infants show the appealing action to attract the parents' attention. So the 9-month-old is more active, like this one. The increase of the action occurrence probability is the increase of the contingent responses, the increase of the expectations. So that's a predictive learning or some prediction or some contingency is one of the other very important aspects. Of course, in this simulation, we do not have treated some attention mechanisms or the gaze information. These are the very, very important one. Okay, so the discussion too is like this one. And the first study I have shown the very fundamental of the neural structure and then 2 states, stable and unstable. So we may apply this kind of 2 states to some situation, the still phase experiment. So before the still phase, so the very stable situation happen. That's a stable. And we can prepare the many modules here may correspond to each of the subnetwork. Okay, this is a stable situation. On the other hand, unstable one is that readiness going down, and then agent try to communicate with the appealing the movement something. In this case, some kind of unstable or more global connection. Even though each module has its own computational model, but everything together working to obtain the caregiver's attention and so on. Of course, there's a big gap between them, but still there's kind of analogy. Okay, so therefore, a neural mechanism can be applied to this kind of some social interaction. Okay, so another one is still phase experiment. This is the dual MEG experiment, the hyperscanning. So we have the collaboration with the brain scientists or the researchers of the MEG scanners. So this is okay. As long as we know, this is the first device, first place to measure simultaneously of the mother and the infant in one sealed room. Okay, in one sealed room, 2 scanners. One is for the baby, one is the adult, and then we measure both the brain activity together. And we set up some video system, so the mother can see the baby can see the mother, each other. Okay, so we have some preliminary experiments. So we have shown the view each other, and also independent movie. Okay, so we calculate the face-to-face experiment, like a still face experiment. the real-time mutual gazing, and independent moving. The right motor area of the parent, the power decrease in the alpha band. The more collector is the mu wave band. Okay. The correlation between power decrease and the AQ score. AQ score means the level of the ASD. Okay. So high AQ score means less mu wave suppressions. So usually the mu wave suppression happen or closely related to some the middle system. Therefore, in this case, so mother and the infant both, maybe AQ score is high. It's sometimes difficult to interact each other. But as the AQ score is very low, so mu suppression happen. It means the middle system may work together. So this is a first trial, still preliminary and in preparation. But anyhow, this is one of the aspects, the support. Okay, I got it. Yeah, I finish. Yeah, in 5 minutes. Okay. This is one of the examples with some collaboration. Of course, in words, the modeling and verification is not yet, but it's one of the aspects. Okay. Okay, so this is the final one, final topic. Okay. So far, we have shown some experiment or the simulations, but also we have developed some rare robots. The Julius group is ICAP. ICAP is a very famous one. But we developed the more realistic one. This is just we say the affect. The affect is also Italian name, right? Yeah, we love Italian. Okay. So not only the appearance and also movement, but also the physical interaction with a real child is imitated. In the video, you can see that very soft the movement by pneumatic actuators, and also the dynamic range of the movement is very close to the baby. So from there, we'd like to have some physical interaction with this robot. Not exactly this structure, but we have done some experiment of the ideas as an infant-detected speech. So we're as a joint research with a researcher of the RICAN, and they are professional of the voice speech analysis. So we set up this affect robot and the real mother. The real mother tried to teach something. And in that case, maybe we found that so the mother shows infant-directed speech to the robot, or robot-directed speech is much more than infant-directed speech. So we need more analysis, but this shows that so the affect can be some potential to as develop a simulator to study how the caregiver interact with the robot or interact with the babies and so on. Okay, so summary on the future issues. Of course, today I have shown that very simple simulations and very fundamental the neural structures. Of course, how to design the robot emotion is one of the issues. And maybe the day before yesterday, we have some general audience and something, the boy asked us, can robot feel the pain? That's a very, very essential question. And we answered that the robot should have the concept of the death, something, okay. Anyhow. So lack of the homeostasis is in the body is kind of the emotion. Adaptive behavior by a brain network is Damasio mentioned that. And it's the classical work, pioneering work is Boston University, Ogata Sagano, is they have shown the robot homeostasis and self-preserving architecture. Pioneering work on the Maple. The interesting thing is that the best behavior for this robot is sleeping. But our, maybe we are against it. The falling is a leading cause of the accidental injury and death in the children under 5. But still, the children, the baby, try to explore something. The machine learning and the development community attacked this, how to design the integrated motivation. Language is another issue. The studies assessing the severe phonetic patient had reported normal theory of mind processing. However, the language property is needed in higher empathic social context. Rather, empathy and motivation may accelerate the language learning. Today, we have not mentioned about anything about the hormones and the neurochemical compounds. The oxytocin is very famous for the emotional empathy, and also dopamine, maybe the cognitive empathy. So the emotional empathy sensitivity and the cognitive empathy capability to characterize the empathic disorders. So we suppose that in the computational model, maybe these hormones and the neurochemical is kind of the game control in the modern sense. Okay, the summary. Architecture for the neural dynamics is the fundamental information structure for affective cognitive robotics. That is a summary of the first study. Of course, the first study does not mention anything about affective cognitive, but it's some structure may suggest this kind of things. Second one is an intrinsic motivation model based on the relatedness is one example, which could be implemented by the neural architecture. But still, there is a big gap. The affective and the cognitive developed robotics should establish the basic principle and the approaches more precisely. Okay, so myself and also Julio, the propaganda of this is a cognitive robotics, cognitive development robotics, affective and cognitive development robotics, but we may need more precise, principle and approaches to the, for the young researchers to start some interdisciplinary studies of us. Okay, so this is an acknowledgement. So there are many people, especially some of these kind of staffs and the students and many other members. Okay, thank you for attention.
Thank you very much, Minoru, for these interesting presentations. Are there questions from the audience? Yes, this one. Okay.
Well, thank you very much for this very interesting talk. As a cognitive developmentalist, I was interested in your outline of cognitive developmental robotics. And I had sometimes the impression, not only in your talk, but in general from those people who are not psychologists, such as also medical doctors, engineers, and so on, that often the approach to cognitive development is rather descriptive. For instance, a typical 5-month-old baby looks at her hand moving. I wonder whether a better collaboration could arise if there were also more interest to theoretical constructs. For instance, in that domain, Piaget old concept of a schema as a transferable set of reactions, and the concept of coordination of schemes. If a scheme is considered as a psychological unit, then also coordination of schemes becomes a relevant concept. For instance, infants younger than 5 months can move their hands and can look at things, but they cannot do two things at one time, moving the hand and looking at it. So being able to do two things at one time, that is to coordinate two schemes, becomes a relevant construct. And so I wonder, and I would like to ask you, what is your approach, what is your feeling about cognitive developmental theories and cognitive developmental constructs or models? Thank you.
Well, thank you. Thank you. Very good questions. Of course, one of the aspects we are lacking is that the collaboration with the psychologist. Of course, some joint research, joint study with the psychologist happen, but it's not so easy all the time with them. Is that therefore some meeting and discussion and so on. So as you mentioned that, so the development process is very variations, and as I have shown, there are many pathways. And also everything not together. Sometimes some aspects are developed better than others, and then interfere each other. So at this moment, I'm sorry, I cannot show them some very beautiful theory to explain the development. My impression is maybe it's very difficult to specify only one unique principle. Instead, we may have some variations or some, obviously, the conceptually, some chaotic trace something might be possible. But for us, we have to decide the details to control the movement of the robot. Therefore, we need a more precise theory or precise principle to, to collaboration with the psychologist or the neuroscientist and so on. One of the big issues for us now is that I have many postdoc students, different discipline. They have their own discipline, fight each other. So it's a headache for me. I expect to collaborate each other, but now they are fighting. So yeah, of course, young researcher, it's very important to make achievement in one discipline first. But we need sometimes we discuss it with the jury. We need some more fundamental structure or the education structure, curriculum, to start interdisciplinary study from the beginning. So now just start each discipline first and then merge. But maybe we need something much more fundamental subject first to study something. Therefore, yeah, as you mentioned, we have the big serious issues of this one. But therefore, there's a summary of my third point is that we need more precise and principle and approaches for the young researchers to follow this one. Did I answer to the questions? Sorry.
Are there other questions? Yes, please.
Thank you very much for the most stimulating talk. This was excellent. So it's maybe related to the prior question, but it goes in a bit different direction maybe. So you talked the whole time during yesterday's session about cognitive robotics. But from the work that you showed in terms of development and the formalisms you'll be using, would it be more interesting to look at more the neuronal science, or to look at neuronal robotics, if you will, so to link the brain science directly more to robots? Then, so there's a link, a stronger link, and there are kind of formalisms in terms of how brain links to behavior rather than how cognition links to behavior, and which is much closer to kind of the perspective that you have. So I don't know whether there are any collaborations that you have with kind of more neuronal side, basically, kind of neuroscience instead of cognition.
Yeah, so actually we have a group and also the collaboration with, actually today I have not shown there are more imaging studies of result. So one good news is now we are doing the collaboration with the imaging studies about the brain scientists and so on. But the bad news is it's still difficult to share the goal. They have their own goal, imaging studies and the nature and the science and something. We are the robotics researchers, not nature science, but the build the design or something. But sometimes, the difference happen. But we have to overcome this difficulty. Therefore, we need a more unified concept of the goal to be shared the many other disciplines. But still now we are struggling with this one. Julia, you have some points?
Yes, I mean, these two questions are in fact, I think, very crucial and key observations about, this idea of establishing interdisciplinary groups. And both of them are very well placed, and this is, pointing out what are the main difficulties in establishing these multidisciplinary groups. I mean, it is, in my view, we have had a very interesting experience in collaboration with Klaes van Osten, for example, and we were able to go at the level where we were designing experiments together, because the models that we are proposing had some kind of holes. So in order to fill these holes, we need to do an experiment, and Klaes van Osten helped us and did that. And also with neuroscientists, with Luciano Fadiga and his group in Ferrara. But I mean, we have been working with them for 10 years, and it takes time because you have to overcome a period where you have to give more than what you get back, and this can be a long or can be a short period, but you need to go through that period. You need to endure your interest in this kind of research, and I think that this is fundamental. I mean, I appreciate your distinction between neuroscience and cognition. I mean, with neuroscience, we are more used. We have robots. We are, reactive. Sensory motor coordination. We have models which mimics oculomotor control and all these kind of things. But I think we need to go further. I mean, this is. We have not solved the problems, of course, but we are at a stage where if we don't add a new ingredient, we are stuck. I mean, we can have faster robots or better models, but still this idea of trying to see what is going to happen in the future will not be possible to address.
Yeah, so not that there are in the world neuroscientists, but Yuki Nagai is a joint research with the patient itself, the ASP. So that's another aspect. And because the patient is very, very subjective or something, the claim. But what is the object? What is the subject? It's a kind of issues. So there, I suppose maybe that's one of the aspects of some joint research.
Yeah, I mean, just one thing. I mean, very often people ask, what are the results of the collaboration? And the results of the collaboration very often are not specific products. Like we have papers, of course, we have algorithms for robots, but very often the exchange is through the general idea of how the system is built. This idea of mirror neurons, for example. I mean. For my personal experience, changed the idea of how an artificial intelligence system should be built, and it came in the group through talking with Luciano and Giacomo about these aspects. So it's a sort of a serendipity, So I think that it is very important also to have physical places where people stay together, because very often you get ideas just by trying to understand what is the point of view of the other people, and not only in front of the coffee machine. There is this idea that there is a magic coffee machine where you share your ideas. It's not enough. I mean, it's just the beginning. Then you have to stay together longer and discuss about science, without having the fear to. Saying stupid things, so without having the fear to demonstrate all your statement, like in a scientific paper you have to do, to go ahead and put a hypothesis. So, anyway,
yeah, we have many issues. And we expect the young generation attack these issues.
Yes. So, are there questions? Bruno, I don't know if you want to say some final words or...
Okay, so may I show the 1 minute video? This one. Yeah, to celebrate this conference. Okay. Thank you.